I would love to see it in the public sector. I mean, saving people's tires is awesome. It's just, and looking at why no one's doing it now, I mean, we've all but decided just the current magnetic systems are just, I mean, if at Harbor Freight you can buy a rolling thing that's like $30, it's like, I know that it doesn't do anything.
We did a team retreat out in Ponderay, so we were like Sagal out on the water, and it was
beautiful lake house.
Man,
stunning. It was like 1980s. What was it? Scarface, the movie.
That's what it looked like.
You would walk in and expect
money,
to see cocaine strewn out. There was no cocaine. Nobody does cocaine, but you would think that it was that vibe.
Yeah, 80s cocaine money is what it looked like. Yeah. It was kind of industrial, but it was on the water. It was super cool.
You had it for the weekend?
Yeah. I mean, I love Coeur d'Alene Lake. I've been on Coeur d'Alene since like 80s. You know, we had a place out at Silver Beach, you know, a long time ago, back when they were still like pulling log booms and tugboats. But so I really like Coeur d'Alene, but man, Ponderay is something different.
Yeah, it's cool.
It's massive.
And especially where we were at, I mean, we were west of the Long Bridge.
Yeah.
On the river, really, but it's so massive right there. It still looks like a lake.
Right.
And then you can pop right into, you know, just cut under the bridge and then you're in the main body of water.
Yeah,
it's cool.
That you talked to Brad on the phone because he's doing something. So he's just a couple years behind you when making the transition coming out of Canada down to the States, and their place is in just west of there. So it's just a cool spot. I mean, if you don't have anything that ties you to like a major metropolitan area, like a business or something, that's really a sweet spot. You know,
isn't it like 100 miles long or something?
Yeah, the lake, and then it's the 6th deepest in the country. I mean,
they test naval subs there.
Yeah,
or
sonar. What they do is it's all diesel boats up there. So diesel boats are awesome because they just charge on battery. Prepare yourselves for this one. You're gonna nerd out on some stuff. I understand like 10% of what Evan says when he gets going talking about tech, but yeah, diesel boats are great because you run them, you charge a battery, they're super silent. So when you're testing sonar down there, you're in a lake, so there's no biologics. If you get in the ocean,
are there though, Eric?
Well, I ever heard
it's pretty deep.
Yeah, but
it could be some things.
The ocean gurgles and burps, and there's weird noises down there when you get really deep. So testing sonar in the ocean is tough, but lakes are great. It's super cool.
I can't even like wrap my brain around how deep that lake is.
Yeah, 16 or I think it's 16.
I mean, if you looked at if without the water in it, it would be such steep. You know what I mean? Because it's not. There are parts that aren't that wide, and it's so deep. I mean, it would be such steep cliff faces.
That's why
it's crazy.
Have you been to Eagle Boat Launch yet, or Farragut? Nope. Oh man, or Farragut State Park. You can.
It's on the way, like by Athol, right?
Yeah. So you go out to Bayview. Yeah, you go out to Bayview. So you go up to Athol, go east, and then you drop right into Bayview. But you can see why it's so deep because those huge granite sheer face cliffs just jet straight into the water, and they stay that way, and it's just got to go down to a point. It's kind of nuts. There's some bodies down there, dude. That's where my brain goes.
You can't recover a body that deep.
They have robots. Robots that do it, and they'll usually bring them up to a depth that you can snag them. I had to do I ended up being a recovery out at the end of the docks in Bayview. And that can get pretty deep.
Gets deep there too.
Yeah, I mean, Ponderay gets deep fast, but that was one of those. That was sketchy because I had no idea what the depth was. I was like, oh,
just keep going,
fixing to find out. Yeah,
Eric loves a good adventure.
Yes, that's true, especially if it's on a boat.
Especially on a boat. Yeah.
There it is, dude.
I gotta let this go. I gotta let this.
No, it's all good, man.
Hey guys, before we get too deep, make sure you hit follow or subscribe so you don't miss any of our latest North Idaho experience content. And if you're thinking about buying, selling, relocating, or just exploring North Idaho, reach out to our team. We're proud to be one of the top-rated real estate teams in North Idaho with the 5-star reviews to back it up. We don't just sell homes, we help people experience North Idaho. Our contact info is in the show notes. Now let's get back to the episode.
That's awesome.
No, we've been excited to have this conversation for a while because truly it's fascinating when you think about it. It's really simple in a lot of regards, and then other ones it's not. But even cooler, you're kind of like a self-taught engineer with this stuff, so it's neat.
That is the cool part, right? I love science. You came out of the oil fields in Alberta, right?
Yeah.
That's how you got your start. Were you always into science, or Like what happened? Did you see a need and then you filled it? Like what? How did this start?
I think just mechanical things and solutions. I mean, I made collages of lawnmowers when I was a kid for some weird reason. I would get the Sears catalog and just love engines.
Yeah.
So it was always just kind of the mechanical interest, and then probably boredom too. Like, so I was a power engineer by trade, sitting at the gas plant. And if you were exceptional, you would work 4 hours out of the 12, like going and doing tours and checking your equipment, right? But the thing's designed to self-run. Mm-hmm. So then you can kind of picture the Homer Simpson job at the back end of that. You're on the computer a lot and you're just kind of surfing around, and, you know, it's just boredom. And I like to do things, build things. And so at that time, I was just looking at it, things in like Alberta oil field that say we call them jerry cans. You call them that here, fuel cans, gas can.
Yeah, gas can. Yeah.
Or propane tanks. And we camp a lot up there. So it was like, you're always carrying one of those things. And at that time there's got to be a better way to secure these things. Like they go rolling around in the box of your truck. And so that's just where the magnet idea started. It wasn't that I grew up loving magnets, although everyone thinks they're cool and you play with them as a kid, but it was, there's got to be a better way to do this. And I'm also one of those people that I like my truck pretty pristine. So drilling holes in it was just not an option for me. And that's, you know, I can get into the whole long-winded thing, but that's where it started, because magnets were a good option to secure something without drilling holes. So that's kind of like where the curiosity started.
Have you ever had any formal schooling? I mean, did you go to college or anything, or was it just like high school right into the oil fields?
Not for that. My education was in oil and gas, kind of, I guess, the secular-ish side, which is just power engineering. So working around, I was certified to work on big boilers and gas plants, power processes, and all that kind of stuff. As far as the engineering side of like magnets, no formal training in that way. We've hired engineers though that, you know, obviously have this stuff that's
can put their stamp on it.
They can put a stamp on it.
Yes.
Yeah.
Absolutely.
There's some smart people out there.
All right. So you started securing gas cans and trucks.
I wanted to.
And
I started going there, and then I ran into the thing that most people run into is like, man, this can do anything. You know, we just kept running into this thing that, hey, if you have a magnet that's strong enough to do real work, it's very, very dangerous. Very, very dangerous. And electromagnet, for all the obvious reasons and many more, was just not an option for me. And so we started, you know, everyone convinces you in the beginning that patents are everything. And if you've ever watched Shark Tank, there's like two schools of thought on that. Kevin O'Leary's like, patent everything, soon to the Stone Age. And Mark Cuban's like, build a business and a brand and get your product out there, right? But at the beginning, you know, we're like, hey, it's technology. So we did patent research. And so at this time, we pretty much knew every switchable magnetic technology out there, or the wannabe ones, let's say. And so we just kept going, okay, we see this big gap. Someone's got to fill this thing, because there's all these applications on the table that are just completely unmet. And like when we start nerding out about it, we've done it many times. It's like, you could do this. And the answer is yes, right? And so that's where it started. It was just saying, hey, there's all these problems that are unfulfilled. So it started as sort of a truck and securing situation, and it just evolved into there's bigger fish to fry kind of thing.
I totally get that, because anytime we start playing with these, I'm like, whoa, you could do this with it.
Yeah.
It's almost like analysis or paralysis by analysis. Like there's too many
100%.
options, right? So you have to just narrow something down.
100%.
That would be one of the big challenges. Okay, which way do we go then?
Oh, yeah.
Right?
Mm-hmm.
Where it's like, all right, let's focus over here. And then I have squirrel brain. So I'm like, ding.
Yeah, well, for me, I'm like, obviously you just make a fidget spinner, because that
100%.
that would be
solve all
that
at
would
once.
be fun for me.
Yeah.
Perpetual.
Just
fidget
play
spinner.
with here while I'm talking.
Yeah.
But yeah, they're incredibly cool. So what? And just to break it down, I don't know any of I don't understand the technology myself, so I'll give you my dumbed down version. You've created a mechanical switch for a magnet to turn it on and off,
Essentially.
basically.
Yeah.
Right. And there are things. Obviously, electromagnetic magnets exist, but they require power. This does not require power. That's the coolest thing about it.
Yeah. Permanent magnets are what powers it. And the material advances in the last 50 years are tremendous, right? In neodymium magnets, people know them as rare earth magnets. But then it became, how do you harness that power in an efficient way where you could do real work with it, right?
Mm-hmm.
And that's a challenge. And actually, magnetism is just electric charge in motion. Like, that's what magnetism is. Electricity and magnetism are the exact same thing, just wearing a different hat. Like, they're just analogous to each other. Mm-hmm. So it's kind of odd that a permanent magnet has these, but it's at the electron spin level. So it's just embedded in it, these things are rotating, creating this strong force. I will just say out of the gate, everyone always goes, oh, you should make a perpetual motion machine. And it's like, no, it's still not possible. Magnets are very efficient. They got all this free energy that we can't, it's not really free energy, but it is continual. But as soon as you extract energy from something, you're still removing it from that system. So anyway, we're not trying to make a perpetual motion machine in any way.
Good to know.
It's yeah, there you go. But yeah, so that's essentially what we do. We take these incredibly strong permanent magnets. We could use it with less strong ones too. And we find a way to harness it in a way that's useful for the application. So like each magnetic layout, even though it's got the overarching same tech in it, will be very, very different. One of the things we do, which we actually discovered while we were in Canada talking to everyone, anyone that would listen to me that I had a technology, I was calling them. Yes, I can build you that. Yeah, I can do this, And it ended up being that a company that distributes airport equipment was like, hey, we got a list of basically 15 things you could do. But if you could do this, we could sell 1,000 of these, let's say. And it was picking up foreign object debris on runways.
Yeah.
And so that's one of the things we really did hone in on. But that being said, the magnetic layout in there is tremendously different than one that you'd see in one of these smaller switches. Like getting 90% of the way there is easy. It's getting the last 10 for like a useful application. That's, a lot of failing forward and iterating and then learning how to build it and harness it and control it and all those fun things.
Yeah, but that FOD application is, there's so many different private airports, military, all of that stuff. It's pretty nuts. It's just, you told me a few stories about that where you go out and say, just let me run it, right?
Yeah.
I'm not going to get in front and sell you. Just let me go. You just swept it with your sweepers. Let me just go run it real fast and see what we come up with.
Yeah, it was funny when we delivered the first unit that was a prototype. It was an interesting year because the year before they had record cumulative snowfall. The next year they had record low cumulative. And then right before we got there, or right after we got there, it was a record in one dump. It was just 3 years of these sort of records. Anyways, because it was the year they had no snowfall, and that's where they gather all these bristles from trying to cut the ice, they said there isn't any FOD on the runway kind of thing. Like you don't need to sweep anything. We're like, well, let's pull it anyway. And you know what? Let's turn it on for fun, right? And so in when we interviewed the director of operations at the time, he did that quote, like, we found needles in a haystack. There wasn't supposed to be these bristles on the runway after a full season barely sweeping, and they still ran their own magnet sweepers, and we picked up just tons of bristles.
Yeah, buckets full.
Yeah.
So is that where a lot of this debris is coming from? Bristles from sweeping the runway?
Yeah, a lot of it. So they're limited on how much potassium acetate they can use, a chemical or sand. Like they sort of balance those things. And so they've tried to go to the poly bristles because the metal is damaging. In the FOD industry in general, a lot of people are like, well, why don't you pick up rocks? It's like, well, okay, we're really good at magnets, first of all. But then second of all, the most damaging FOD that really will
metal.
It's metal, right? And a lot of people think everything has switched to composites and aluminum. That's not true. There's a lot of steel on an airplane.
Right.
But that being said, these metal bristles they're not going away. They've tried to switch to poly. It doesn't cut the ice. Right. And so in a lot of these places where they have to maintain the runway for, especially F-16s, their engines are very low to the ground. I've seen images of, bristles that are embedded in a turbine blade, like 1.5 inches.
Dude.
Yeah.
That's
You're
crazy.
talking multi-million-dollar aircraft.
Oh,
yeah.
The engine alone, I think, is $8 million.
Yeah. Oh, they're nuts.
Yeah. It's nuts.
Don't even get into like F-35s.
So, and these, that would be applicable on civilian runways too?
For sure. Yeah. They're using, like, the winter airports are the ones obviously cutting ice, but there's construction seasons. There's, we're developing a product right now for the ramp, and the ramp would be analogous to, like, or the where the airplanes dock, the ramp, the apron, they call it different things. That's where they find the most FOD. And so we started with like the Lamborghini version, like the one that's like, pull this thing 60 miles an hour and pick everything up.
Right.
And now we're sort of evaluating the product line and going, okay, where else can we address this? So the ramp area, we're doing a smaller version that you would depend on your truck, let's say. And they do find a lot, like zippers, you name it, like in that area, right?
Mm-hmm.
So this is scooping that up at 60 miles an hour.
60 miles an hour, yeah.
That's wild.
We can, like, I've got a graph, but we can do, I think the one I simulated up to like 77.
Yeah.
They're not doing that speed though. Like they're not going to 80 out there. Their air traffic controller would be calling and be like, get the heck out.
Slow it down a little bit. No, but that's wild though, because you brought up the speed thing before. Because you think about a runway, and there is a certain minimum speed you want to be, especially if you're going over. I mean, it's a magnet, right? So if you've got metal reflective lights out there for a runway, and you're going over that, and you're going too slow, that magnet's going to do what magnets do.
It's actually interesting. They have what's called light cans that they bury that are flush mounted in the ground, and they've tried to switch to aluminum. A lot of them, some of them haven't. But when we drive them over there, if you're going 20, it's like bogging the thing down.
You can
20 miles an hour it's not nothing. If you go watch something drive, it's like, okay, that's pretty fast. But also they use steel bolts, and the one gentleman was like, hey, that's great. If those bolts actually, they can fatigue over time and snap. He's like, that's a perfect way to find out if they're broken. We'll rip it right out.
Oh, okay.
Okay. So how powerful the magnets on the sweeper?
It's pretty wild. So we talk like a good magnet term is Gauss or Tesla, which is a pretty common term. I like to talk in pound force just because it's relatable as a human. So that's probably about 120,000 pounds of pull force over the 10-foot sweep.
Oh,
yeah, it's pretty wild.
How far away? Like if you put a bolt 10 feet away, would it?
Well, we actually dial in for that. That's what's really unique about, and it actually was probably a year and a half of simulations and building physical things, testing them. To pick up debris at a distance is a challenge, right? Like if you just go brute force and go a ton of magnetic volume, yes, that works. But magnets are expensive, and we're trying to optimize for safety and all these things at once, and switchability and all these things. But in our layouts, we're about 3 inches. Well, if you park over it, you could easily do 3.5, 4 inches maybe. And a bolt for sure. Like picking up the little bristles is challenging because if you had this 1,000-pound magnet and you put a tic tac on it, you can pull it off. It's not going to feel 1,000 pounds. You need to have enough steel to grab that it represents all of its force capabilities. And that's the same in the debris. So you're picking up these little 10 thou thick bristles that have very little volume of steel in them at speed, right? When you grab a bolt or a washer, it's no problem, right? That's basically what the existing tech is picking up. It's the larger stuff, let's say, but definitely not at speed, and definitely, not every time.
So guy sweeps the runway. Now he can walk behind this machine, flip a switch, and the metal just falls down.
Yeah, and we're running it with an app now. So you can run it from the cab, you can control it, and you get feedback. So like, hey, am I in the safe position lifted high? Am I lower? Am I on? Am I off? And then you've got a debris drop mode. So you get back, and then you make sure. We had to build interlocks so they don't accidentally drop it after they've picked it up on the runway. But yeah, ours is the one you can switch so stuff falls, and that's why it's safe. I think there was a situation where they tried to ship I call them dumb magnets. I'm not trying to offend magnets, just ones that don't switch. But they tried to ship those up to Alaska through Canada to the Air Force up there, and they banned them just because they couldn't be switched on and off, right? It was just a safety factor, even though they're not even that strong. But it was just that thing of a permanent magnet's a little bit scary. Even a weak one, it's like
I mean, you've got this 1,000-pound one here, and we were just playing with it, trying to pull that. I can't even slide it, nothing.
Yeah.
So if you got your finger in there or something when that thing,
it's pretty remarkable. I mean, I think interacting with the magnets, like you can hear 1,000 pounds, and that's obviously a lot. But when you play with them, or when you assemble these things, I mean, it's wild.
Yeah.
Well,
you gave me those little ones, those little tiny ones, and I cannot break them. Like they are so strong. It's nuts when you think about what must be going on in there. For those out there that are, let's just say me, can you explain like layman's terms difference between what you're calling like a mechanical magnet and then like an electromagnet?
Yeah. Electromagnets, so they were invented in something like 1820. And all it is just you have a core element like iron and you wrap it with coils, right? And so again, electromagnetism it's the same force, but wearing a different hat. And so magnetism is just electric charge in motion. That's like the distilled version, right? And so that being true, that they found that they could do it really well. Like they put current through, and it goes by how many ampere wraps, like how many wraps you've got around it kind of thing. And it's not really changed. The only thing that's changed since that time is material sciences, superconductors, like that's what an MRI uses, let's say. and things like that. So an electromagnetic, as soon as it's just got a core element, you put a charge through the coil and it magnetizes. So that's simple. So like anything you're powering right now has magnetics. Like they're in everything in this room.
Nuts. So what's the difference between that and then just a, manual throw
switch? So an electromagnet is coils wrapped around a core element and you put charge through it. Ours is using permanent magnets, which are, a group of rare earth elements sintered in a certain way, magnetized, and they stay that way. And we use those in what we call an array. So we just have repeating structures in a certain layout optimized where we've got 2 rows, let's say, and you mechanically adjust the position. Permanent magnets don't turn off. Our job is to give them a happier place to go, and we do that. So we say, hey, even in some cases, we don't switch them fully off. We leave residual for the client and say like, hey, this might help you align it, or this might give you, make sure you can feel
but you can manipulate it. Yeah.
We're manipulating. That's what we're doing. We're not even really bending physics, but the magnets want somewhere to go. We're trying to give them a happy place to do it. And that was a challenge, right? They're very strong. Like once they're in their array, they seem really happy and innocent. It's just getting them there was, a lot of work to figure that out.
Yeah.
And it's interesting too. I got to say, like, there's people that did switchable magnets before us. So you see these, in like patents work for 20 years. They give you 20 years and they're meant to be a teaching document. That's why they exist. They give you 20 years though to make your money, let's say, and then it's public knowledge. So I'm bringing that up because there's a company called like MagSwitch, and they've got the switchable permanent magnet. It turns on and off really easy, and it's strong-ish. But what would typically happen is you would take 3 dumb magnets, let's say, that are 100 pounds of force each, just for an example. You would put them together, try to pull them off. That'd be 300 total. You'd add them up. 300 pounds would be too much, let's say, to remove. So you want to put them in a switchable array. No problem. So they've done this. But what they take is they take the 300 pounds and they actually turn it down. So they derate it, let's say, to, I don't know the number, but let's say it's 220. So it went from 300 to 220, but you're pumped about that because now you can use it. Our tech, you actually take what the magnets have, you get switchability, and you dial it up to a pretty extreme degree. So you take more force than the magnets have on their own, and you retain switchability.
Crazy.
Sounds like synergism.
That's magnets go a little too hard.
Yeah. So the difference in ours is we're using permanent magnets and a mechanical manipulation. Mm-hmm. Our tech though could be half electro if we wanted. Like the overarching layout is what is unique to it.
Is that like this one right here?
Nope, that's still permanent. That one's just got a servo motor that does the manipulation instead of your hands.
Yeah, and that's what I want to drive in. A servo motor that switches a manually switched magnet is not it's not an electromagnet. Just because it introduces a little bit of electricity for a switch, that's not the science behind the physics behind it's completely different.
Yeah, you're just manipulating a position, one quick input, and it stays, one quick output, or whatever.
That's why it's just for practical application, because you and I have nerded out about this before. When people are talking about a concept, perpetual motion or a rail gun, right? The thing that they're talking about with a rail gun, I mean, that's what's all over, sci-fi. They're using electromagnets for that, right? Where does that fail?
Well, it's fails in a lot of places. They're remarkable, but they're incredibly volatile. Like I think some of them they've tested, they did 3 runs and the barrel was torn right apart.
Really?
Yeah, they hit Mach 6. Yeah, like they're wild.
Shit. Yeah,
they're wild.
And that's using electromagnets.
So I heard stories where they tried them on aircraft carriers. Don't quote me, but I think the challenge was it took the whole ship down. Like the amount of power you need to put through that thing to accelerate at that speed it's nuts.
Even with a reactor or 6 on some carriers.
It's nuts. And then so an MRI is an interesting thing. When you charge an electromagnet, as you guys know, if you turn the power off, then it dies, right? Mm-hmm. If they can superconduct it, so they put liquid helium in there and it goes to basically essentially true zero, like minus 267 degrees or whatever it is, like absolute zero. So in any case, they do that and the current never shuts off. So an MRI, they bring a machine in, they charge it, and the current just sits there running forever and ever. That's what they do. So it's an MRI is never off. The only reason they do that, they have like a vent pipe that they like heat up the helium and it goes out. If someone's pinned between where like a chair pinned them in the wall, that's when they'll discharge it. But the amount of power they put in still is dramatic. So some people have talked about, hey, can you use that in like a launching situation where instead of taking the ship down, you store this power into a thing, but there's a lot of downfalls in that, right? And you're also dissipating it at such a fast rate that, I mean, man, it's just volatile. It's heat. It generates just so many bad things.
Yeah.
You know,
Yeah.
it's if you've ever watched one, you can go right on YouTube and watch them shoot. You're like, okay, how do you do that? Right. Cause it's scary.
Yeah.
Yeah.
A lot of power in a very confined small space.
Yeah.
And it sounds more like the material doesn't hold up. What you would have to build it out of, you're applying so much pressure and force into that.
Oh yeah.
That the actual mechanism itself doesn't hold up. The materials don't hold up. They're not strong enough.
Yeah, no, it's wild. Like Mach 6.
That's freaking nuts, dude.
They've done successfully. They probably have some that maintain, but it's a problem, right? Like sometimes you hit these solutions that sound amazing, and then it's like, but how much engineering do you need to do?
I have such a basic brain when it comes to that I think about things like we're putting a lot more things into space now, right? It seems like a really good tech for that because of the lack of friction. Because if it's generated using magnets, there's got to be a way to do that where you're almost slinging it into the atmosphere as opposed to exploding it into the atmosphere.
Totally.
If that makes sense.
I think that's been in sci-fi books for a long time. I think the challenge is you're applying so much G-force to whatever you're throwing that, you know, if it's sensitive electronics, obviously I don't think you could do that at all, but sensitive electronics, I don't know if that would work to harden it against that acceleration. I don't know.
Well, the human body is always the weak link. We already have, I mean, some of our jets can outperform the limitations of the human body. I mean, they can throw G-forces that we just simply can't sustain.
Maybe if you had a really long track so you could accelerate at a slower pace and then hit that top speed right at the moment of launch.
Right.
Maybe that would work, but
unless you're...
What do I know? I've just read a few science fiction books. I'm not a scientist.
Top Gun Maverick, dude. He can sustain.
Top Gun could handle it.
Space is a good place for magnets, though. Yeah. They suck in heat. It's called their Curie temperature. So it's like 770 degrees C, like the average neodymium magnet, they'll outperform. They'll demagnetize. But in space, they're actually even better. Yeah.
Can they be used for heat dissipation?
Probably in some way.
Yeah.
Depends on the application.
Yeah.
Back to the railgun thing. Sorry.
No.
Is there a way to do this with mechanical switched magnets instead?
I mean, I think anything's partially possible. It just, you know, we've looked at like moving mass is what I would call it, right? And it's a big thing. Elon's currently trying to use a coil or railgun on Mars. I think is his thought to move things around, just moving mass, right? Maglev uses what's called a magnetic river technology.
Yeah, because I guess you wouldn't have to do it at Mach 6, right? Because you could just push something up and over, and if you could time it.
That's right.
Right. Well, maglev trains already exist, and that's just, I mean, they're slowing that they're not launching them at Mach 6.
I think, isn't California doing a really good job building one?
Yes, they've nailed it.
Gavin.
Yeah, absolutely. If you gave that to the private sector, imagine that. That would have been done in probably 2.5 or 3 years.
Yeah,
right?
but, you know,
at
I mean,
a fraction of the cost.
It just depends how much money you're willing to put into them, because they are no way around how expensive a maglev train is.
Right.
Oh, it's wild.
Just pure and
like
material.
The Shanghai one is 30 kilometers. I think it was like 1.7 trillion or something.
Oh boy.
Oh my.
Takes a long time to pay that off.
Like it's not nothing. You have to keep everything super like they put the technology in the train itself so that they're not putting that all on the track. And I think they're using liquid nitrogen instead of helium, which is cheaper, but it's orders of magnitude cheaper, and it's still in the like it's wild. Yeah.
So you talk about the rare earth materials required for a, what do you call that? A pure magnet, right? What materials are you talking about, and where are we getting it?
Yeah, this is a big misconception right now. So rare earth materials, everyone thinks it's a funny misnomer because they are called rare earth, but people think the materials are rare, but that's nowhere near true. They're everywhere. It's the process to separate them, because in the lanthanide series in the periodic table and where they originate, they're all so dang similar, and I'm no chemist, but to separate them is like 800 or 1,000 different chemical processes. That's filthy, it's dirty, and it's hard to do. So like every process, you only get a little bit closer to what you actually want, your neodymium. And so that's the main reason. And China does 91% of the globe's separation.
Wow.
Yeah.
Man.
Yeah. So like the mining's great, and everyone's like, oh, well, let's go find more. It's just that's not the challenge.
It's not like you dig up, oh, here's your pure magnet. It doesn't.
No way.
No
way.
North Idaho Arms is a proud sponsor of this podcast. North Idaho Arms is a locally owned full-service gun store in Post Falls, Idaho, founded under one guiding principle. They are unapologetically pro 2A. The owner, BZ, is a friend of ours and is a 2A rights absolutist. North Idaho Arms throws a flaming middle finger to all unconstitutional gun laws. Handguns, rifles, suppressors, magazines, ammo, complicated moves, estate transaction. BZ does it all. And yes, you can purchase some of these items if you're a Washington resident. Go see BZ at North Idaho Arms, Post Falls, Idaho.
But then the other thing is so what's called coercivity, that's just a magnet's ability to withstand demagnetization. Is that important? Highly. So in motors and things like that, temperature is one that brings them down, or it's basically their ratio to width and like if they're wider than they are thick, they have a very high chance of demagnetizing, and there's numbers they assign to these things and calculate. But coercivity is additives, and these additives increase the magnet's ability to not be demagnetized. Why does that matter? Right now, with the new tariffs and things, China has said you don't get any heavies. So I'll quote magnets and they'll see HREE, heavy rare earth elements. Nope, not happening. So you can get like a basic N52 grade, which is a great magnet, strong, whatever. But this is just something sitting on a table without like a ton of heat around it and like ton of motion. And so that's how they're cornering a lot of things right now. So there's more elements like dysprosium. There's a list of heavies, and they're saying no, you can't put those in. So the heavies are another challenge on top of like, hey, how do you get the sintered material or the rare earth materials in general? So it's a pretty big deal. Like the U.S. uses right now 12 to 13,000 tons a year of magnetic material, and our market is growing by a 5x by like 2030. Like all the EV motors, defense, they're in everything. In your house, there's over 100 magnets that you don't know about.
Like
this microphone has magnets.
Appliances? I mean,
yeah, your microwave is a big magnet.
Oh,
Yeah.
right. Okay.
Yeah.
Magnetron. But this microphone, your headphones, your earbuds, that's all neodymium. From your fridge magnet to the doorbell, things like that. They're in everything. Your cell phone, I think there's something like 90 magnets in there.
What?
I'll bet they're in boats.
Definitely in boats.
I bet they're in boats.
That's why Eric likes.
Well, I guarantee it. They're in alternators for sure.
Oh yeah. That makes sense.
They're all over.
Oh,
I mean, your ABS
HVAC,
system.
Yeah.
In your car, your
That
ABS
motor.
uses magnets. Everything.
And I guess you're right. Like you mentioned, the EV vehicles and hybrids, everything. That's all increasing dramatically. The production of that. Those are
and it actually stalled though, right? So because you couldn't get these heavies, you just can't get around the fact that a magnet needs higher coercivity, right? So, and then there's other magnets called samarium cobalt, and they're way better at withstanding that temperature, and they're even more hard to acquire.
Right.
Yeah.
Just a longer process, or
yeah, it's just it's where I think it's the samarium. Those in that case, I think it's where the samarium is actually a little harder to come by than like these are called ND fab, neodymium iron, and boron. But yeah, like those samarium cobalt, I think it is the materials in those that are a little harder to come by.
Where do United States and Canada stand as far as mining for those?
Mining's good. Like, so I think the government acquired all of MP Materials, a U.S. company, and they literally have said, we'll take 100% of what you produce. And so they're getting better on the mining. It's the processing that's challenging. There is a mine in West Texas that's doing a great job, and they're coming out with sintered block. So the sintered blocks, essentially you take the minerals, mix them in a powder, and then you put them in a furnace in a shape, and for long and short of it, you sinter it into a block. Then you would just cut, coat, and magnetize and sell like specific ones. But so the additives and their formulas and their process is very important. Like there's technology there. There's companies trying to do, there's one in Minnesota, and I think it stemmed out of a university. They're trying to make iron nitride magnets. It's cool. It's needed. I'm not sure where, like, I mean, I think, you know, how most things are, they're 3 years behind or something. And I don't want to quote that or say anything bad. Just, I hope it works out. Just neodymium's remarkable. It's just dirty to make these magnets, and
yeah,
we're starting to take it more seriously in the U.S. side. It's just not an overnight process.
Takes a while to change the industry. Well, and especially when you get into the defense industry, that could be, it's a hard one to break into. There's a lot of red tape. I mean, I don't even feel bad saying it. People listening don't get it. Like, a lot of it comes down to, some of that's return on investment for elections and stuff like that. It's not always the best product on the table.
I've seen that. Since the 2016 Trump administration, I think they stepped into where I think it's Wyoming and a few, and I think it is that MP materials that, don't quote me, but it was that thing of like, it is a little dirty to mine. I don't think it's as dirty to mine as it is to do the separation. Yeah. But that was even thrown up red tape. And so
might even be dirtier to secure a contract.
Yeah. I mean, it's wild though. Like the tariffs and the rate of increase lately is nuts. I think it's something like 37% just duty and tariff you'd pay getting it in now. From China. Like, I think there's some sintered material in like Korea, but that doesn't have the duty and stuff. But the Chinese stuff was just such a cheaper product. Right. But now there's the tariffs, and then there's a new law coming in January 27. Where it's just like anything defense related. Nope. The answer is no. It's not coming from China.
So it's going to have to be domestically produced.
Yeah. So if you're producing it domestically or wherever, you get this block of sintered material, cut it, and you say coat it, and then magnetize it? Yeah. How do you magnetize it?
That's probably the simpler portion. Like, you have the right equipment, and you're just adding the charge, and it stays that way.
So you're just hitting it with an electrical charge. Yeah. And it stays charged, and that's how it...
How long does it stay charged? Is there like a dissipation rate? I always think about like nuclear material where you have decay, like eventually...
Yeah, it's interesting. So it's something like less than 1% over 100 years.
Wow. Really?
Yeah. But like, again, there's other ways to demagnetize. Like it's the permeance coefficient. And that's, again, the ability to withstand demagnetization. And there's ways that if you put too much force in like one direction, or the shape is like wider than it is thin, those are things that can demagnet. But just sitting there on its own, they're not just decaying.
Are there similarities between a magnet and a battery? I mean, a battery has charge as well. Is there different?
They'd be different. That'd be, I think, electrical. Like, these are, it's actually, in a permanent magnet, it's interesting because magnetism is electricity in motion. Like, that's what it is at the most basic level. And so that's an odd thing to say about a permanent magnet. Right. Right. Because it's like, well, who's charging that thing? But it's at the molecular level or whatever. It's the atomic level. I'm no scientist, but the electron spins are in motion.
Wild. Yeah. That seems wildly efficient, that if it stays that for 100 years.
Yeah. The technology is, like, in the last 50 years, or even, I think even 20 years, the technology in the permanent magnets alone. I mean, that's why your earbuds are that small. There's no way without
magnets.
Yeah. Or the rarer stuff.
Well, and you talk about, people always, joke, we need a perpetual motion machine. Well, I mean, what if you just have a really, really efficient one? And it seems like a good way to do it. You don't need perpetual, but just one that's really, really more efficient.
1% degradation over 100 years. Like,
that seems pretty efficient. Yeah, it seems good.
I think you're right. I think it's an interesting thing, because that's probably 25% of the time people want to nerd out on magnets. They're like, build a perpetual motion. I'm like, A, it's not possible. B, I'm definitely not the guy to do it. B, it's just a challenging, I think the people missing the perpetual motion thing. It's one thing which hasn't been done yet, to have something spin forever, but now extract energy out of it to use it.
Yeah, exactly.
And that's a whole different thing.
Right. Yeah, because you're not just asking to put it in motion forever. You're asking for it to generate more power and then extract that from it.
There's no free lunch. But there is wild inefficiencies. I mean, heat is the biggest one. So electromagnetics, they don't just fail based on if you lose power, if you lose a certain, like, they've got to be a rectified, like 12 or 24 volt, let's say. Like, if that fluctuates, they don't work well. But just like alternators in your car, you lose a phase at a time. I mean, these things degrade. There's heat. It's electric current going through. But heat is a big byproduct. Like, the overhead crane stuff in the junkyards. Like, I mean, I think they run at like 600 C or something. Like, it can be pretty crazy. So heat just degrades stuff. It's a byproduct. It's just like burning wood. Like, you lose that energy from heat. So yeah, so it's these byproducts. So they've done really good advances in like superconductors and the material sciences. The magnet itself is pretty unchanged. It's literally barely changed just they've learned ways to insulate with thinner materials on the copper so they can get more windings. Like that's where you get more power from.
Right.
And then there's some really cool advances in motors. Like I think it's a Mercedes motor, uses a company called Yasa or something. And they use an axial flux motor. So it's on the flat surfaces, not going circumferentially. So you're able to get a ton more surface area, but then you're dealing with other issues that they're solving in unique ways. So like the best people aren't pretending that the physics isn't a barrier. They're just addressing like the challenges and like, let's say the byproducts, the heat or these things that are robbing you of energy.
Right.
But like these people that are doing remarkable stuff that's nowhere near like perpetual motion, right? But it's advancing and using physics to your advantage.
And making it more efficient.
Heck yeah.
And again, perpetual, probably not attained. It just seems unrealistic, but something that's really, really efficient where we can use less explosive energy, which is still what we use almost exclusively, or heat, explosion or heat.
Well, that's part of the technology too, is like, so for example, our tech, I've looked at, can you use these same magnets? Like if we're talking about what's a solution that would be an incredible business, right? You would go pick the application that no one's done, do this, and it's like, that's cool. But like, what if you could take a certain layout and you could get rid of the need for these high coercivity magnets that right now you can't even get, those heavy rare earth elements? Like what if you could what if you could make it that way? You make a more ubiquitous motor that's made with like more readily available materials.
And increase the scope, right? And in effect, because you aren't waiting for those, because you see what the bottleneck is. The bottleneck seems to be those, what you call them, HREs,
right.
or
that's right.
That seems to be the bottleneck. So if you could make it more practical for everyday use and application, making things more efficient, that seems to be a pretty damn.
Well, it's part of, I think, business and defense and all of it is supply chain. Do you have it? And magnets are just, they're so ubiquitous. People just don't realize, like, our life, if we didn't have a magnetic field of the earth, you'd be dead.
Right.
Like it's continually bouncing the solar winds off.
Right.
Like it protects us. Or we would look at like Mars, they had a magnetic field. I had read they had a magnetic field. Once it died, then it just heated up. Right.
Nuts. So, and if that's the case and it happens naturally, is it possible when we're talking about, it gets into crazy stuff, but like terraforming, part of that would likely be some sort of artificial magnet to protect from things like that, because that's how you would likely control.
Be a lot of magnets, bro.
Yeah, control
a lot of magnets.
I mean, maybe yes, maybe I don't know. I mean, because until you explore that tech and kind of get to the bounds of, the limitations, I don't know.
That's neat. And by the way, that our Earth's magnetic field comes from the iron churning in the earth. Because it's magnetism,
like the core of the earth that is hot.
Because of the movement stops and magnetism stops.
Huh.
So it's pretty interesting. They've actually found that even like cows, they line up. They've used satellite images, and they're like, why are they lining up that way? They're aligning with like magnetic north.
What?
Yeah, and
birds, right?
Birds have magnetite in their beaks, and so they've done experiments that seems pretty mean, but they'll like cover them with like different magnets, and they don't know where they're going.
Whoa. Oh, it trips me. The bird migration thing just trips me out.
It's what salmon. They do the same thing.
Too,
yeah.
huh? Dude.
Yeah, so that's how they find their way back.
So you got to think, I mean,
to the exact same spawning spot.
Have we had that ability in the past and,
I wonder.
And we've lost it?
Oh, we 100%, if we ever did, we've lost it now.
Right.
All right, absolutely, we've lost it now. We've over-magnetized ourselves.
Well, is that why some people have a really good sense of direction?
Maybe.
Is there
off.
something to it where they can sense it a little bit more than most?
I wouldn't write it off. It's in nature.
I don't know. Then this is weird that it comes on the heels of you getting me into this whole quantum entanglement madness, where you can take a atom and flip the polarity from literally across the galaxy, and it'll switch it over here if you split the two.
They're concentrated. They're entangled.
Nuts.
And then you start talking about big magnets and big switches, and it's crazy.
Evan, can you hand me that one over there? It looks like a hockey puck.
Yeah.
Yeah. So if you're listening, this is one of Evan's. It's a little bit bigger than a hockey puck, and then there's a part that you can turn on it, and that's the switch. And when I turn the switch, I can take the metal disc off the bottom like easily. It has a slight.
That one's residual.
Slight residual.
8 or 9 pounds or something.
Yeah, but you can move it around, and then you just turn this again, and it's like locked on. I mean, it's not as hard as that one, but it's still it's locked on there. So what's the process going on inside of this? We touched on it a little bit earlier, but
there'd be a stationary layer. In that one, there'd be a stationary layer and then a manipulated, we call it top layer. That's actually got 3 rows of magnets. There's some more kind of advanced stuff. And again, it really just depends on what you're trying to achieve. That we just built for something. All that's good for is to show what it can do.
Mm-hmm.
It's not really application based. But each layout is very, very unique. I mean, I would say the foreign object debris stuff has been the most challenging. Like if you said to me, I want a switch that's 3,200 pounds, which by the way, I've got a new tech. I developed that in that same size. I can get 3,600 pounds.
What?
What?
Which is I think something like a 4 or 5x of what the magnets have on their own that you could harness.
You could pick up a damn car.
Yeah, it's wild. You'd be limited by the materials.
Yeah.
Yeah. But
yeah, that would just rip apart.
Yeah, I mean, it's probably possible, but that being said, yeah, it's pretty interesting. Like there's different layouts for one. So FOD is probably the most challenging. You're picking up at a distance, and magnets actually suck at a distance. The reason an MRI room is so scary at a distance is just the size of that magnet is insane.
Right.
And it's never off.
Right. The way you describe that makes a lot of sense because I've seen those horror stories.
Oh yeah, there's true.
They
deaths
can't
in
shut
an
it off.
MRI room.
That's why I never understood. It was like, why not? Well, you cut it off. It's an electromagnet, but now that makes sense.
It's not.
Yeah.
It is, but it never, like the heat does. There's no heat. It's superconductive, and that current just sits there running. So they discharge it by heating it up, and then the helium goes out like a tube out the. It's only for emergency though, because then there's no free lunch. Like to turn that thing back into a magnet is very expensive.
Right.
Yeah.
No shit. So I mean, is an MRI strong enough if someone has a lot of iron in their blood? Like, is it going to manipulate and move the iron at all?
I don't know that an MRI is, but a magnet. They've done it. They did it before on a frog. They levitated a frog with 1.6 Tesla or something.
Because of the iron in his body?
It's because of the water. So everything's actually, it's called diamagnetic. So we are diamagnetic technically. We repel magnets technically, but you'd have to have tremendous strength, like a very, very strong. And a frog is mostly water.
Yeah.
So they floated it.
And it survived?
Yeah, it survived. It was fine.
That's freaking wild.
Or at least they said it did, yeah.
Yeah.
Its insides were jello, but...
Yeah. Other than that, it's totally fine.
But yeah, like everything is apparently diamagnetic. So that just means, yeah, it's slightly repelling magnet. So if you have enough force, then you could levitate stuff. It's funny you say that thing. People are like, oh, well, why don't you just do that with maglev? It's like, because that's very, 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 very expensive.
Right.
Yeah. Permanent magnets are not cheap, at all.
Yeah.
And they're only increasing in every year they'll start using more.
Sounds like especially in the next couple of years.
But it's just going to go up.
If we switch the spigot off from China that's producing 91% of the material required to make them, yeah, it's only going to get more expensive.
Yeah. So, and I think they handle 61% or something of finished magnets out the door that you could, buy in a shape.
Right.
But yeah, like 90 some percent is their raw materials.
Well, I don't see us getting past the EV era anytime in the very near future.
No, and that's one example, but like think of a wind turbine, like they're in everything.
Mm-hmm.
They are in everything. There's something like 90 in your phone. They're not going away. They're your hard drive in your computer, magnets, your credit card, magnets.
Yeah.
Everything. This microphone.
So this back to the hockey puck here.
Yep.
So are the magnets inside of it just like rectangular, normal looking magnets, or
those ones are? Yeah.
Yeah.
But we do custom magnet slots too.
Huh.
Yeah. So it's a combination of magnets and steel.
and
it's what you call an array. So it's like the way that you lay them out and then the optimization. But the softwares that they have nowadays are remarkable.
I was going to say, because if you change the shape of it, if it's not just your typical rectile,
excuse me.
We've not worked with those.
There's probably
a rectile.
There's probably a use there too.
There's an application there.
There's an application.
But it's not the rectangular magnets, and you start changing the shape to make them like concaved, and then you start aligning them with each other. That's going to change the way they interact with one another.
Yeah,
that's what you're talking about with the software. Micro adjustments are going to completely change.
Oh yeah, it's wild. It was really fun on the software. There's something called optimization module, and our engineer, I had him play with it once, and it was like, you would tell it an input. Like, so let's say that thing takes 1,000 pounds to turn. like just for example, you would say, get that number down. So you'd select this number, be like, tell the computer, this is your goal. Do this. You're allowed to play with this, this, and this. Right. And so it did. And one of the things it played with was shapes, and the magnet it came up with was like not even possible, but it was like this atomic looking, you know what I mean? But it's still wild to think like you can get there.
Right.
You know, like
if
the
you
soft.
if you could cut it, if you could produce it and find enough.
That is a crazy software, dude.
Oh yeah. It's wild. Right. But you know, and that's what's really neat. But I'll tell you, even then, like magnets are so in our arrays, they're so counterintuitive. Like, I mean, I've spent years simulating like the foreign object debris one, which is also funny when I look at the effort or at least like the claims of some of these, like, let's say a roofing nail sweeper. They like claim that it can do a 6-inch pickup on a 2.5-inch nail. And I'm like, no, like I don't have to simulate that to know that you're so far away from that. But they rate it where the magnet's standing upright. So like that's the best place for a pickup where like all the lines would converge. And even then I'm not convinced it can do it. So it's just funny in the magnet world and like product development, just how people don't put any like third-party testing and no ratings on it because they're just they're so underperforming.
Right.
So that's like when we started with the Runway sweeper, it was like the goal was, do you want us to go 10 kilometers an hour faster, or like do you want us to pick this stuff up? And so we just chose let's make this thing history, you know?
That's wild to me. I mean, I absolutely see the application. I just look around a house and you see what a Roomba does. We're not far away from that, where that thing could go out and run in the middle of the night where there's no ops, there's nothing else, and it's just got a planned system, and it could go perfect speed, perfect app, perfect everything, right?
Yeah.
And just get every piece of it in
A runway Roomba.
Well, I mean, because honestly, it seems to me one of the most limiting factors, because you are dealing with magnets and they can be dangerous, and they break. And you just had to go to Duluth, but they break, right? So that's usually human input.
Yeah, just like in the oil field, like it's not usually equipment failure.
It's human failure.
It's human.
Yeah.
But you know, I think it's interesting in the FOD space. All the money and the grants, not all, but like pretty much everything I've found is going in detection. It's just a funny thing to me. Thank you so much for pointing out that we have more FOD. Like, who's picking it up?
Right.
Like it's just, I've always found it really interesting. I think I did see a grant where they were looking for like a Roomba or something, but it's just magnetically like the damaging FOD is that, and it's like we just sought out to solve that, and we did.
Can you get a grant if you're like, hey, I'm detecting it while I'm picking it up? I just
maybe.
detected all of this. Here's your pile.
Right. Visually in the pile.
Yeah, exactly. It's I don't know.
I could see that being useful on the side of freeways in large metropolitan areas.
We've been calling the Department of Transportation lots and going like, hey, like,
I feel like they would be all about that. I've spent a lot of time on the shoulders of the freeways, and there's freaking metal everywhere.
Yeah. Well, it sucks. Like, you know, nails in I was at the mechanic shop the other day. My valve stem was leaking, and I'm like, they were asking about the magnet project because I got an alignment before I went for the trailer haul there. And they're like, yeah, we get guys in all the time that are in like, you know, municipalities and construction areas, like 6 nails in their tires.
Oh, yeah.
Like, yeah, why aren't we?
Or like the transfer station, you go to the dump. I've gotten all sorts of shit in my tires there.
Yes.
It's infuriating.
It's all construction.
Yeah, we're working on one that actually is front mounted. So you'd put a front adapter, because like you could put the hanging bar, but that's got a lot of problems for a lot of reasons, you know?
Yeah.
So we want something rigid that you could put on the front, and then, you know, people can like a municipality or something, they could run it. Like, just run it. Like, it costs you nothing, right? And I designed it so it can't rip the manhole out, you know, but...
Yes. Yeah, and you almost put it on the front of a plow truck, you know? So
they've done that, and it's neat.
Double dipping.
Yeah.
I saw a guy do that. I thought it was actually remarkable. One of the smarter ones I've seen. The only problem is it was only for the people that had the snowplow, because it was hydraulic. It had the PTO and all these things. And it was just more than the average person could afford or want. Like...
Right.
So they were kind of assuming if you ran a snowplow on your, you know, how some guys just, you know, everyday citizens will do like plowing of parking lots in the winter for extra money. And so they've installed this thing, and they're assuming those people will do it. But I'm trying to design something where like, hey, anyone can like get this on.
Yeah.
Pick the nails up and things like that.
Nuts.
So the runway sweeper, it's not like your passion, right? That's just,
I mean, yeah,
it's cool.
magnets.
It's really cool. And it's a very viable business model. Is there something out there that you're like, I really want to mess with this? thing.
Yeah, I want to play with motors.
Okay.
I want to see if we can solve some of the supply chain, like the shortages. Like, can we decrease the need for those like the heavy rare earth element stuff in motors, like ubiquitous stuff, right? And then in general, I'm always looking at, can we get the same performance using less magnets, right? They're expensive. And so we've succeeded at that in like a ton of ways. And so I want to kind of aim that towards like more everyday, bigger problems that are ubiquitous to our world that aren't going away. You know, everyone wants to put people on the moon. It's kind of like, can we find a better way to make things more viable for our country and things like that? Mm-hmm. And it is very interesting to look at moving mass, like the maglev stuff. Excuse me. They use magnetic river technology, but what can permanent magnets do that directly compete with what electro did? There's actually something, this is interesting, called an electropermanent magnet. And so you would think it's best of both worlds. It's neat. They use them a lot on robotic grippers and stuff, but so one portion is a full-on electromagnet and the other is like a weaker type of permanent magnet. So anyways, when you put the input, it is just for switching. So it just switches the top one, let's say, and it stays in that orientation. So it's not constant power usage. Problem is you're half a strong one, and then like the permanent magnet, sorry, I meant not electro on the bottom, and then you're half like a much weaker one.
Yeah. So
like our tech will still be far more like high gradient strength. Like it'll be more performant, but there's really neat things people are doing. Mm-hmm. It really is. And that iron nitride is cool if it does happen in the US. They're called Niron, and it's like iron and nitride. It's like super readily available. And they've successfully done some magnets. I can't see the performance being that of neodymium. And so many things have that performance baked in. You know, it'd be like going backwards in anything you do. You're like, well, I'm not going to take 100 horsepower less just because you say that it's built here.
Right. Well, it seems like they're trying to solve some of the same problems you were talking about.
Which I think is awesome.
Where it's readily available, and maybe you get it to a point where it's not going to have the same application. Well, it reminds me of I was on subs, and the Russians made a titanium submarine, and that thing could obviously go deeper than anything else that we had, but it could do it about 5 times, and as compared to high yield steel, because that will go down there and flex. So we could go down, a fifth of the depth, but you could do it thousands of times, right?
Yeah, there's nuances to designing things that matter.
Yeah. Absolutely. But if there was like good practical application, it doesn't have to be as strong as maybe, I mean, in my mind, that's the way I look at it, where there would be everyday uses for it. Maybe it is for something like a bad application, but a microwave or something that's used every day when we don't need all of that.
Yeah, you're still advancing.
Yes.
Something. Yeah. Yeah.
That'd be cool.
Yeah. And I don't know more about them, but yeah, but for something like the runway sweeper, just, you need that.
Oh yeah.
That high gradient strength, but like yeah, to your point, it'd be awesome to be picking up stuff across, right? I mean, I think we've talked to the DOT in many times and just kind of just had, easy convos like, hey, tell me, like, do you feel this problem? One big one is like the roofing nail companies. Like we're designing one of those now. We're just building it. It's just, they're going, yeah, like these don't pick up anything in the grass, like just none of them.
Right.
It's like, okay, well, we can do that. So
were you talking earlier? Can you make one strong enough to rip the nails right out of a roof?
Oh, I probably could. I think they don't want that. I think they want
you just cleaning up outside the job
cleaning up outside. You could though. Like,
I was thinking of when they demo a roof and they're having to pry it all up. If you could just run that thing over and then shove the shingles down the side.
Interesting. Hey, I'm always up for that stuff.
Yeah, but imagine if there's any metal in the attic or anything else, like it would
good point.
Real funky, real quick.
Some kind of who knows?
Exactly.
That could be a problem.
Well, and I just wonder if Department of Transportation does feel any of that, because it's one thing at somebody's house where you have a customer and you're putting up a new roof and they're pissed that there's nails in their yard. You're going to feel that. But Department of Transportation, how much do they care if you flatten tires? Because all that does is make a tire company more money. And
well, then that's just it in business. Like, who's willing to pay for the problem?
Right.
But I mean, if you could make it, they're already running sweepers frequently. If you could make an attachment that went on the front of the sweeper truck,
it'd be great.
Just snatched up all the metal.
Will it, if you took it to Seattle, will it pick up hypodermic needles? I could absolutely see.
That would be cool.
I could see a practical application for that. Like, could it pull it out of somebody's arm? Could you do that and just like hold it up sideways as you drove through downtown Seattle? just yanking needles, just thack in the front of them. All right, that'd be kind of legit. That'd be kind of fun.
Changing the world. I think, I mean, magnets are neat. Like, I would love to see in the like you said, I mean, the the debris pickup is cool. Like, it does solve problems, and you know, if even one fighter jet is saved by our tech, I mean, that's a great feeling, you know. And I think it's one of those things that it's a funny industry. Like I said, they're all doing detection, which I still just scratch my head going, guys, like, great. Like, one of you must have solved finding it by now. And there's good companies and everything, but I don't know what that really helps you. Like, the way that the airports run, from what I've seen, it's like it's all speed, right? So downtime is huge. Like, I think Dubai is the most expensive runway, and I think it's like $1 million an hour.
Wow.
Or something like that, their main runway. Like, now the rest aren't like that, but I think Dallas Fort Worth is in the tens of thousands.
Oh yeah.
So it's like downtime matters, right? So it's like if you had a product you could run that, like for example, they find the rock. Like, what are you actually doing about it now?
Mm-hmm.
You know, so I don't know how that really fits, but obviously there's a reason. But at the same time, we wanted something like, hey, you just grab this thing, you go, and you know you picked it up. Like, you don't have to second guess, and we're gonna get third party data. Like, we'll have the supporting evidence saying like, hey, here's what it really does.
Mm-hmm.
But so yeah, that like to your point, like it's a cool need. Like, you know, it's not nothing. Like, yeah, you're picking up debris, but you know, like I said, if it helps national defense or national security, like, that's amazing.
Mm-hmm.
Have you looked at local airports here, like Coeur d'Alene Airport? Do you know what they use out there for their FOD cleanup?
So they're under the same FAA standards, but it's a funny thing, and I've still yet to. I can't give this conclusively, but everyone follows the same regulations, but no one really has a solution to pick it up to like a certain degree. There's another one that is like a friction mat that does work well, but it's like it wears out and you have to replace it every season. But that being said, they follow like their FAA inspections. And we've talked to some of them about like, hey, instead of buying this unit, like, would you want to do like a service sweep, you know, a few times a year? And a lot of them are like, yeah, that might be cool.
Oh yeah, like charge.
Yeah, come out, pick
time.
it up, you know, clean it up. Because some of the problem with FOD is it'll blow back around, or like springtime, a lot of times it'll surface.
Oh yeah.
You know, and then the wind will carry it on there and things like that.
Right, seasonal for sure.
Seasonal, yeah. So we're looking at that.
How do you do your R&D? Like, I know you have a really cool machine. Tell me about that.
Yeah, so our process is, well, definitely in the failing forward chapters, it's instead of making something that's really just generic, try to really dial in on the application. And so we prefer finding partners in like their industry. So like for the runway sweeper, it was like we partnered with an airport and be like, tell me the problem. And it's not just as simple as pick up debris. Okay, what speed?
Right.
Who's pulling it? How are you going to pull it? When are you going to pull it? How high do you need to pull it? Where else are you running it? And all these things that go into it. So we kind of step back. Once I have that, then we go to the simulation software and we go, okay, like, let's build this to the 95%, 98% quality. I mean, it's pretty remarkable. We've done enough closing the loop, which would mean I simulate, then I do a physical test. I compare that data. And we've done enough of that I trust our simulations to a pretty high degree. Mm-hmm. And then we get into the design phase, and we've just learned we have to do our own manufacturing. So we manufacture in-house right here in North Idaho. So it's like, hey, we need to build this. So there's just too many factors that go into this stuff that I don't source it out. So we'll do a prototype in-house, and then we'll stand into the more manufacturing side of things, material selections and all that stuff. So our process is pretty much the same, like identify the problem and then work through magnetically first, and then you'll design around the magnetics.
Right.
And then you've really got to consider, like, for example, the runway sweeper, you don't want to be dropping debris as well. Like, if they did hit something, are you going to bust a bolt out? I mean, that's bad news bears. Mm-hmm. So we have to think about that when we design how, like, where's the failure points? Like, if they ram into this thing, like, will it fail in that way? So you take the magnets, you design around them. We build in-house, and we do a lot of like physical testing with stuff to make sure it's there. A lot of times you build it and you see something that you thought you should have saw before at the computer, and you can correct for it yourself, you know, kind of on the fly. So our process is pretty, like, it's a challenging one, you know, through the simulations, especially with the debris pickup. It was a lot. Like I was saying, if you said I need a switch that's 1,600 pounds, it's about this big, in about 2 hours, I could give you like 90% of the way there. Mm-hmm. But then the FOD stuff took like a year and a half of simulating. Yeah. It's just it's a dynamic problem.
Well, right? How wide is the
sweeper? Magnetic package itself is 10 feet.
Okay.
plus trailer.
Is it just one switch, or is there
one
to do all of it?
Yeah,
at the same time. Okay.
Yeah, and that one runs on hydraulic, and we're gonna get away from hydraulics. Just in the winter seasons, I've had in the oil field hydraulic hoses blow up on me. It's no fun.
Yeah.
But we keep advancing the tech in kind of unique ways, and so we've got new solutions on that. So it'll just be ran on a simple motor, and we want to build a back end as well in FOD because you're finally mitigating it.
Mm-hmm.
So like where you can weigh it and you can like track your stuff right in an app and things like that. So we might even look at partnering up with detection because it doesn't hurt us in any way.
No, and it's almost confirmation of what you're doing. I mean, those two absolutely should work hand in hand because they can check immediately after you go.
That's just it. We have so much confidence in what it picks up that it's like, yeah, of course.
Yeah, but it'd be cool. You know, what passes are more successful during what season? What conditions are the best for picking it up? You know, and if there is anything funky, you're going to see it right away.
There's probably patterns too where it ends up on, because of the jet wash. Yeah,
totally.
Exactly.
And I love that. You nailed it. Exactly what I was thinking because it's that thing where you can just get an AI system to cross-reference it with snowfall or like all these fun things that are because then you're helping them even more. Like when do you want to run this?
Yeah. Or the planes that generate the most, right? And even though a lot of it's coming from foreign stuff, they might kick up enough that's around that they're bringing more onto the runway. So then you say, all right, if you're flying KC-130s, then you're likely going to introduce this much. You want to run this 3 times a week instead of once.
I mean, heck, maybe if it's even an employee that just is very careless about what they're dropping, right?
Yeah, absolutely.
So, you track that, weigh it, and all those fun things. I would love to see it in the public sector. I mean, saving people's tires is awesome. It's and looking at why no one's doing it now, I mean, we've all but decided just the current magnetic systems are just, I mean, if at Harbor Freight you can buy a rolling thing that's like $30, it's like, I know that it doesn't do anything, like it's not going to solve any problems, especially at speed. So like I said, that's where we went. And so, I will say leapfrogging into our next chapter, the FOD study has been cool. It's dynamic, right? And so we've got some tech in cool areas. We've played with stuff. We never built any products yet. One thing that is a cool thing to think about for magnets is in, let's say, the non-destructive testing field, which would essentially be like checking a weld. Is there porosity or cracks in a weld? And they use magnets all the time. They use an electromagnetic yoke. It's these 2 arms. They turn it on, zap. You find a gap you put some oil that has magnets in it and it pools if there's a leak.
Oh,
right. It's neat. It's called MFL, magnetic flux leakage. So we can do that with permanent magnets. The ones that they currently use are just dumb magnets. Again, I'm not trying to offend them, but they don't turn on and off and they're limited because they can only be so strong or you'd never get them off. Right. And so we played with some stuff there. We've done things. We even have a patent on where we rotate magnets so fast that magnetic flux that goes into the surface doesn't fill your bucket. It'd be like skipping a rock on the water. If the rock sits there, it sinks. Mm-hmm. If you skip it fast, it sits on the water. So you get to use less flux and get more performance out of it. That's basically how those AC yokes work. So we've done that. So I'm just kind of rapid firing some cool things that magnets do that people don't necessarily think about.
Yeah, so it'd be application in a lot of building processes.
A lot of building. Crane inspection's huge, right? And so my understanding is they don't bring the AC yokes up there all that much. I don't know a lot about it. Or penetrating with the permanent magnets, penetrating paint is tough. So we essentially, anything permanent magnets can do, we've increased just the performance on it. But that being said, we've had some different things. So we've got magnetics at distance, which is FOD, right? You can create a high gradient field at distance, and there's very unique ways to do that with our layouts. In fact, we've got a couple new layouts that are even better at it recently. Frequency, we can generate frequencies with the magnets, which is the MFL that I was just telling you about, right? Like you can spin these things, right? High gradient strength. In some cases, it's just that FU force that's super important. It's like, could a magnet do that? Yeah, but it needs to be orders of magnitude stronger. It's like check, right? Switchability on off. And so even right there, like that's, 4 different characteristics. I'm kind of now going, okay. And then there's the manufacturing piece. Like, do you have the ability to actually build and test these things? If you kind of add those things up in a bucket, now we're at that chapter where it's like, I think we're into the advanced space. Like now, what do we want to play with? But I'm really glad we didn't too early because it is really challenging. It's really fun to say out loud, I want to build a better generator. But I mean, there's some remarkably smart people that have worked on generators.
Right.
And to walk in and be like, I'm going to just displace them in a day is just crazy talk.
Yeah.
But, you know,
trial and error, man.
Trial and error.
That's a great teacher.
It really is. It's just that build it and
yeah,
fail and build it and fail. And,
right.
and, you know, we were lucky. Our prototype, that was a cool feeling. That thing worked right out of the gate. But that was years of culmination kind of coming into it. But that being said, just talking about our next chapter is adding all these things about magnets that aren't maybe super obvious, and combining them in something unique is really neat. Like moving mass would be cool. Like that's what Elon wants to do. Like, you know, on Mars, like things like that. So advancing material sciences, I guess you could kind of say that for our want to eliminate the need for these high coercivity magnets.
Yeah.
Or at least improve that a little bit.
Right.
But, yeah, there's some fun advanced stuff that we're talking about, and it's really taken that magnets are it's super obvious to think they're strong, they grab things, and then when you start diving into like how do you make that useful, that opens up even more ideas in your head. You know?
What's the name of your company?
Lantha Tech.
Lantha, Lantha.
Yeah, Lantha, and that comes from that lanthanide series in the periodic table. That is really hard to separate those out.
Yeah,
they're like twins that you can't tell apart, but like they do matter in their element breakdown, let's say, and then
when you get into splicing the different characteristics of each and what you actually need.
Yeah, it matters. Yeah,
that's cool.
But because they're so similar, that's why it's so messy, expensive, and crazy to separate them into a useful magnet.
Right. It's just so nuts because you can't. It's just a crazy tech to me because you can't see it. Right, like it's not something that you can.
No,
literally...
I can't quite wrap my brain around. I'm
like
just not smart enough to understand this.
This is wild. I just learned this. Apparently, the only reason you can't push through this wood is magnetism. That sounds crazy, right? Is that because at the molecular level, like the spin actually repels,
really?
or it it creates like a binding force that like the only reason you can't apparently push through this wood is.
To get those to split apart and move.
Is that what gives everything its structure, right?
Apparently,
metal, stone, like it has its own.
Yeah, it's just magnetism is crazy. It's just this inherent force that like they first found it. They call it lodestone, and it was like there was the old people's the sandals. They had like an iron rod, and they stuck to this rock, and they're like, what the heck? And they figured that was from like meteorites or something, right?
Yeah. That's how they figured that. Yeah, it's nuts. It had to be even weirder then because you're like, what is
invisible force? Yeah,
yes,
that's true.
Exactly what
it's crazy too because like we've done stuff with like our version of really strong magnets, trying to see if it'll interact with like humans and things like that. And then our answer is usually no. There's not enough iron. It's like that's actually not true. Like Magnetar is the like intergalactic, magnet that's like trillions of times stronger than the Earth's magnetic field, and if it was halfway between the Earth and the Moon, we would all just like evaporate.
Right. Oh, just pull us all apart.
Yeah. It's just, but like that's how strong it is.
It's nuts.
Well, you blew my mind, dude. Well, boys, we're over an hour now. Believe it or not,
we did a pretty good job.
Time flies when you're talking about magnets.
I know
they're fun.
They're freaking cool, man. They're very cool.
Yeah.
I'm very excited to see what other applications you come up with. And the coolest part is you're doing it right here in Idaho, man.
Yeah,
just another example.
I know there's cool businesses out here.
So many.
Yeah, you're gonna see more fun stuff come out of North Idaho magnet related.
I feel like we need to put you in touch with Ryan Wiggins.
I was just gonna say that.
He was just on the podcast talking about he's got a company that does battery tech, and it's mind-blowing stuff.
There's some smart people out there.
Yeah, very similar. Where it's like, you guys are kind of on the cutting edge of doing some cool stuff, and I could definitely see collaboration.
Yeah,
just the way that their batteries work because they don't. The way that they're retained.
Yeah.
Right?
Yeah.
And how they hold up to extreme heat and stuff like that.
And that's neat.
And he came from a non-traditional background as well. Like he Navy guy. It's like
I'm convinced
he didn't come out of,
The guy that invented the electromagnet was a shoemaker. He was like the shoemaker apprentice, and he just played with it on his own. So, and then he started lecturing on science. It's neat. Science is just observational.
Right.
Right.
Science is just...
Sometimes it's better if you're not in the industry or in like the educational sphere first because you just look at things differently.
Yeah, you don't have that influence, that like traditional influence that might shut that down.
So the same with Joshua G9 Ammo. That dude was working on, he was like metal fabrication and repair on cars. Like he did, body work on cars. And he saw the way the bullets went through, and he's like, "Oh, that's weird." And then
that's so cool,
because you'd think that it's somebody from military or law enforcement. No, he just looked at it differently. He's like, maybe it's less about the material, more about the way the bullet travels through the air.
Right?
You're like, huh?
He'd be a guy to connect with too.
Yeah.
Super cool. Yeah, and that's the way it is. I've worked with both. I've worked with PhDs in magnetics, and I am not going to discount their intelligence. It's wild.
Right.
Like this guy is just like, oh man. But
but then there's the practical application, right?
Oh yeah, he told me that what we're doing now back in the day was impossible. That's what he said.
And you're like, oh. All right.
I still have the drawing where I drew it. Now it looks like what you might expect. Like stick figure would be generous, right? Yeah. But it's like that's where it came from. You know?
Right. But you came at it from a completely different spot where it's like, maybe I haven't been educated enough to believe this is impossible. Which
and I'm okay with failing, right? I don't have the pride. Like I will fail and keep iterating forward. So it's been magnets humble you all the time. Every time you play with them, it's just like these are crazy.
Yeah. You're like a little micro. You're like, God dang it, that should have worked. On paper, that worked.
Yeah. Oh yeah.
It's cool.
Yeah, but it's a blessing how far we've come, and yeah, it'd be really cool to bring more stuff to North Idaho. I mean, and get it out there.
Building cool businesses. We need cool manufacturing up here. I'd rather not have it be all IT or.
Yeah.
Agreed.
Yeah.
Well, Evan Trevor, thank you, brother.
Yeah, cheers.
Thank you, sir.
For coming.
Super cool.
I'm sure we'll have you back because I'm sure you're gonna have some cool updates in the future, and I'll look forward to that.
We have other topics. We have other topics as well. Just not yet. Not yet. Cheers, guys.
All right, later.